Ethan Smith is an assistant engineer in capital planning at San Jose Water. In addition to managing and configuring San Jose's water's PI system, he can explain what that is. His work primarily consists of master planning and management of water facility and sustainability-related capital improvement projects. And he's here to also explain dissolving data streams and this very alliterative pumping pipe performance. Take it away, Ethan.
Thank you, Dennis. Thanks everyone for tuning in. I'm an assistant engineer with San Jose Water, been there for about 4 years, and here to kind of share our success story with the PI system. It's a Viva product we use to optimize our pumping operations to better manage our energy consumption and increase our efficiencies. There we go. Okay, I'll skip this as we had a nice intro from Dennis. Thank you. Quick roadmap overview. I'll just give a brief background about San Jose Water, some of the issues we are facing with pumping and data. The solution that we found, which was the PI system, a little bit on how we implemented and applied that system, some initial results we've seen, and then I'll finish up with some takeaways and next steps, and we should have some time at the end for questions. So if you haven't heard of San Jose Water Company, we are a private investor-owned utility, and we serve the greater metropolitan area of San Jose, shown in that center map there, that yellow highlighted area. We have over 230,000 services connected to over 1 million different people. And to give you an idea of the different source waters we're dealing with, about 60% is purchased pre-treated water from our wholesaler, Valley Water, and that serves the areas shown in green on that map on the right. And then the downtown district of San Jose is where the majority of our groundwater well stations are. So we pump about 30% of our total supply from those aquifers, chloraminate and provide to that area. And then the last 10% is from the watershed in Santa Cruz Mountains that we manage. We have a treatment plant right off of Highway 17 that supplies water to the Los Gatos areas and the mountain districts there. A little bit about our operations to give you the idea of our scale. We have just under 100 different pressure zones of various sizes, and across those zones, 84 different stations that are either extracting and treating groundwater or pumping water from one zone up to another to fill tanks at progressively higher elevations. And then across those stations, there's 204 booster pumps, 89 well pumps, and annually we're pumping about 23 billion gallons. So it's a lot of water, and with that, a lot of issues. I'll touch on a few that kind of spurred us to look into the PI system, and I'll focus on 2021, as this was the year we adopted the system. And in that year, 92% of our energy consumption was coming from pumping. It was a massive amount of energy, 40,000 megawatt hours, over $9 million with the rate at that time. And so it's driving up the cost for us as well as our customers, and also putting a burden on the environment through the carbon emissions associated. It was 2,800 tons, and we pledged by 2030 to reduce our emissions to 840 tons. So looking at that status, we knew something needed to be done, especially looking forward to the projections based off historic analysis. We saw energy rates were going up, and they are going to continue to go up as we've seen over the last 4 years. It's been pretty dramatic with PG&E and most other utilities in California. And then at that bottom graph, you can see our energy efficiency, the kilowatt hours per million gallons that was being pumped was going up. So it's taking more energy year over year to pump the same amount of water. And we needed to act to try to switch that curve around. Another issue we were facing was poor data quality. We had some monitoring, but mostly we were relying on field tests. So an operator had to go out and actually, test a pump and motor, which was just a lot of work. And with limited staff, it was only occurring every 2 to 5 years. And it was a single snapshot in time. But it was the best we had. So we were using that to schedule our replacements. And looking at what happened, it's obvious we weren't making the optimal choices because we were still seeing 5 to 20 pumps and motors fail a year. And you can see on the right, that's motor windings that got burned up. We had no idea that was occurring. All of a sudden, it just shut down and we had to pull it. And it's a long lead time to get it replaced. And so relying on backup pumps, it puts strain on the system, can cause service interruptions, and it's just more costly to do last minute repairs and replacements. And then lastly, we were using the cost estimates from these tests to try to prioritize which pumps we were running, but there's no guarantee that the data we were using was still relevant and accurate. And then last problem we were facing was, I mentioned we did have some monitoring, but the issue was that it was siloed in these different databases. So we have on-prem, SCADA system that has the flows and the pressures at our various pump stations. And then separately in third-party databases in the cloud, we had power, vibration, temperature, or pressure sensors, or energy consumption data. But we lacked a way to integrate it all together to actually develop KPIs from the combined parameters and start making better decisions with this data. And for us, the solution was the PI system. There's quite a few other softwares that do similar things, but this is an Aviva product, which was also the company we use for our SCADA system. So they integrate and play together very nicely. Here's a kind of overview of the or architectural kind of configuration. There's API connections that we're able to use to pull in all these different data streams from, different databases that are in the cloud. And we have, a custom Aviva adapter that connects directly to our SCADA so we can send data back and forth securely. And essentially all these data streams are integrated into a single archive. We can then build a framework on top and associate all these individual data streams to the correct asset, whether it's a pump or a station or a well, and then build KPIs or analytics on top that develop KPIs that we then push out to our operators and our engineers through an online cloud-based dashboard system, PI Vision. And I'll show you a couple of those dashboards here today. And also through Excel, through their plugin, so you can do additional analysis with the data. A little bit on the implementation. For us, it took 3 different dedicated servers and about a half a year to deploy. Depending on the size of the system and your staffing, you could definitely shorten that time frame down to 2 months. And also working with a third-party integrator is really helpful. We didn't have any experience in-house with this system, so being able to learn from that third-party integrator, which is for us Casney Engineering, really helped me kind of take the reins once they kind of helped develop the framework and put us in a position where it's easy to scale and continue to grow it. But taking a look at the framework, you can see there's a hierarchy. And so we have elements, parent elements and child elements. So our station has its own attributes, and then nested within that station are all the assets at the station. And then within each of those, there's a list of parameters connected to data streams. So flow, power, head, those are all kind of under each pump. And then we can have analytics on the template that for every single pump will calculate the efficiency, the cost ratios, the degradation, which is, how is the head different from what the manufacturer said it would be at a given flow. And then on top of this, we can build alerts, which has been a really powerful application. We can get real-time email notifications to our operators and engineers for different events, such as a pump turning on during peak hours. You can see on the top right, it makes a huge difference the time of day when you use energy. I'm sure a lot of us are familiar with time of use. That 4 to 9 p.m. period can be 50% or more higher than the other hours of the day. And then if you use a lot of energy like we do, you get hit with additional demand charges. So you turn a pump one on once, and whatever that, the max kilowatt load is, you get a pretty high fee associated with it. So being able to know that that happened and then tweak the way that we're operating so that we can, make sure we're topping off tanks right before peak hours to let us use that, capacity in the tank to prevent pumps from having to turn on to maintain pressure and meet demands is pretty huge. And then also we can get alerts about the condition of our assets. So if degradation drops below or goes above a certain value, we get alerted. If individual parameters go outside the expected range, we can know vibration's high, temperature's high. We can then send a mechanic or an operator out to investigate and see if we need to pull this pump or what kind of repairs might be needed. And then also if data goes down, a sensor runs out of batteries or there's another issue, we know right away rather than a couple of weeks later realizing we were missing out on data. And then here's an example of a dashboard. I've built out quite a few for operators and engineers. This is what we can see for every single pump. We have kind of metadata at the top. We know when the pump was last on, how long it's been running, and then we can trend and look at any time scale we want up to real time and see what's that efficiency, what's that cost ratio, energy ratios, how much energy do we use during each time of use period. And then we plot the curve and we can see, okay, how is this pump operating relative to what the manufacturer said it should? And then the last few graphs at the bottom will be kind of raw data streams such as flow, pressure, power, temperature, vibration that all have their own alarms on them if it goes outside of what's expected. And last application that has really been a game changer for us is real-time pump prioritization with the cost data. So we know the energy consumed based off our power monitors. We know how much flow is going out. And so we can get that energy per gallon ratio, multiply it by the rate that the utility charges for that unique station, and then send that data back to SCADA. And that SCADA system controls which pumps turn on and when. So we can automatically rank and choose the cheapest, most efficient pump to turn on the most often. So therefore, we're increasing our efficiencies and reducing our energy consumption. And we implemented this ranking and these alerts in 2023. And so we're able to take a look at 2022 to 2023 and see the results of applying this system. And we were kind of shocked at how well it did work. We were looking over the summer months and saw, flow weighted average of $83 per million gallons savings compared between the 2 years. And this is illustrated with the graphs on the right. You can see in 2022, the cost ratio plotted against time is pretty much all over the place. There's no trend. And for 2023, you can see how as runtime increased for individual pumps, which are each point in that plot, the cost went down. So the system helped us run the cheaper pumps more often, and it was a huge change from the year before. And similarly, we were seeing that there was a increase in efficiency. So not only was the cost going down, but our energy consumption was going down. Between the 2 years, we reduced the kilowatt hours per million gallons pumped by 243, which resulted in 5.5 gigawatt hours of reduction in energy, which is considerable. It's 14% towards our goal for carbon dioxide emission reduction. And so we were really, really proud to see that one. And lastly, the peak demand savings from those alerts I mentioned. Our operators were able to tweak when pumps were turning on and then when we were topping off tanks, and we're able to see a $42,000 drop in those peak charges between the 2 years. So just some takeaways to start wrapping up. Water utilities and really any industry or business that has a lot of different data streams that aren't currently integrated can benefit from a system like Pi. For us, it dissolved the data silos we had. let us start capturing, insightful KPIs that could inform our operators and engineers. We had real-time monitoring and comprehensive analysis or analyses that would, be fed into our asset management program so we could more optimally schedule replacements and reduce our downtime. And then we could optimize operations to reduce energy consumption and the associated costs and the carbon emissions as well. And lastly, and this is kind of what we're excited for next, is paves the way for start to leverage AI with all this data and the advancement of AI recently. There's new applications coming online, and one we're particularly interested in is Aviva's predictive analytics. So it uses AI to create a model of every single pump in our system. It knows how that pump should be functioning. It has a huge database of what kind of failure modes are associated with certain trends for certain parameters, so we can get alerts ahead of time of, hey, this pump's trending in this direction. These are the parameters that are going a little bit off. Our system says this is likely a bearing failure or wires overheating, et cetera. And it can actually give us a timeline estimated of when that failure might happen. And so we can really drive our downtime and our failures as close to zero as we can, and just have a really robust asset management strategy going forward. And that's everything there, and happy to answer any questions.
Well, thank you, Ethan. I was reminded about the energy water nexus, right? I know San Jose Water has really been a leader in in just these kinds of systems, as you mentioned. And I mean, even last year, in terms of we're talking about the AMI rollout, and involving metering, and especially in on the private utility side, where it's been generally tough sledding getting things through the Public Utilities Commission. And but it's really great to hear about from an operational standpoint how you've been able to reduce energy consumption. There used to be a statistic about what was it, like 17% of the electricity in California is used to move water. And I mean, I don't know that's an old one, but I don't know what the number is now. But certainly you've been helping to move that number downward.
Yeah, we're really happy with the result, and it's been something that we've been aware of for a while, and it's hard to address, without start looking at the data and really diving deep and leveraging systems that help you, better use that data. And I'm not surprised that pumping uses that much energy in the state of California. It's considerable. I mean, when I saw it was over 90% of our energy use, I was pretty shocked.
Yeah, well, I mean, I think it was like 6% was just to move water over the grapevine.
Wow.
And I know we had Jeffrey Keitlinger talking about the Metropolitan Water District water enterprise and how water gets from the Colorado River to the LA Basin. And unlike the Hetch Hetchy system, which is gravity flow, so relatively minimal, some pumping, but not a whole lot. Everything there, it's all uphill. It's like, it was amazing how much pumping, water went for like a 240-mile trip. There is one question, and it seems like a different system, but how did this affect leak detection?
It's been somewhat of a separate program. We haven't yet tried to integrate the two. we have a pretty robust, leak detection and acoustic monitors on most of our hydrants, and a team that goes out and investigates them. Yeah, that being said, we haven't really looked into the connection between, what pumps are running, and their consumption as a factor in the leaks. That'd be interesting though.
And there's a question about the size of the database.
Yeah, that's a good question. So the way the licensing work is it's based off of the number of data streams that you have. So we started out with 7,000 points, and with the other kind of plugins and connectors, we paid about 100,000, and we've since grown that system to 25,000 data streams. And I think our overall investment's a little over 200,000 for the software. But it's pretty large. We host the archive on a cloud database with Amazon, so we're able to scale up the size of that server as our system increases, which has been really convenient. And yeah, so probably continue to get larger as we continue to build out applications, especially once we get AMI and develop DMAs and start doing more of a water loss assessment using Pi. It'll vastly increase, how many points we're working with.
Well, thank you for coming on and telling us about this. And I see one final question I have to get to it here. Okay, so they were just asking about the type of database, an Oracle database or other. And I think you mentioned that it was an Amazon.
Yeah, the servers with Amazon Web Services, the database structure, I'm not sure if I'm guessing it's proprietary to Aviva.
Uh-huh.
I mean, originally it was OSI Soft, I guess, and then Aviva acquired them a couple of years ago. But as far as their kind of backbone to the database, I'm not sure what they're using.
And I trust it's well protected. We have the former head of Microsoft data center strategy on tomorrow, talking about cybersecurity, among other issues. And obviously, there's been some well-publicized things, I think, in Florida with different utilities and their incursions into some of their internal systems. So,
yeah, it's very much a concern for us. We had to do our cybersecurity team did a deep dive into this system before we adopted and vetted all the connections and the protocols. I couldn't cite off exact security protocols being used, but I know it was approved by our team, so we've had no issues so far.
Great. Well, yeah, thanks for coming on and going through this. It's great to see what you guys are doing.
Yeah, my pleasure. Thank you for having me.
So